Yes, sir.
Okay. So let's say for the cylindrical coordinate one, so you know the generalized heat transfer in the cylindrical coordinate is given by this equation. Derivation of this can be given completely. If you want, I can give the derivation of that. But we want to solve it from here. So this is your generalized heat transfer equation in 3D coordinate for the cylindrical coordinate system. So in this case, again, we want to solve at primary the level because we want to solve the ordinary the differential equation, ordinary differential boundary value equations. So we want to make it to one dimensional only. So in that case, let's say we want to say the radial heat transfer here. So first we have made a constant here, steady state. So the time derivative would cancel. No heat the generation within the material, so E dot the generation we are cancelling. So after doing that, you got the equation number 11. Then after putting a constant totally heat transfer in the radial direction only, so you got this one. Now I have not changed this partial to the total, so this will become actually now the total in the derivative because temperature is only changing in our coordinate system. Now, again, you have taken that isentropic means material. So K is independent of your actually the direction coordinate. So you have taken K outside. K is constant. Sometimes, let's say K is also varying with respect to temperature. So you cannot take it out here. You have to be here. It will not be cancelled out from this equation. So let's say you are talking about constant thermal conductivity. So you will end up this one. Now you can differentiate this and you can rewrite in this particular format that R del square T upon del R square plus del T upon del R. So del will become now the total derivative actually. Okay. So now here you use means again your central difference formulations for the second derivative and your first derivative. Fine. So if you'll do that, so you are the writing for that. This is your the means expression for the second derivative. This is expression ti plus 1 minus ti upon 2c. This is for the first derivative. Fine.
Yes, sir.
So here I wrote fine. Anything? So now you have this. Now again you have to write this actually that c the distance between two consecutive difference point is calculated by this and divided by this, and then you have radii and all this. Then you want to generate spacing between this and calculated by ri, that ri plus I plus c. So keep on adding that c, then you can generate it. So you can come to know by this particular figure that how they see and everything is there. So let's say this is your inner the radius of your the cylinder. This is your outer the radius, and this is the solid material here from here to here. So let's say see the difference between each points here. So you got here, keep on adding, and at last one you are getting here Rn plus 1. Fine. So if you see the practically here, you are getting n number of the difference point between boundaries.
Yes, sir.
That fine. So that way you have seen. Now you can write those that equation. You have the rearrange that for to this one of the side that you are taking I minus 1 at one side, I terms at the another side, and I plus 1. So this is your generalized equations here. Now for this again you will do the same type of treatment as you did the previously for in case of metal bar. So this is now for the cylindrical coordinate in the radial the direction only. So here you just keep on changing your I from 1 to n minus 1 and n. and then you will get your n number of equations. Fine.
Yes, sir.
And then again your T naught would be the boundary, and Tn plus 1 will also be your boundary. So if you do that, so let's say here, so if you can write here, this will give again a clear picture of the previous one. So this is the original picture, the previous one, but the expanded version of this one only. Now what you have there, so this now keep your changing your I. So let's say your I equal to 1, you will get this equation there, and this is your boundary condition here, this one. So let's say we want to solve it for temperature boundary condition first. So let's say T naught is known, so that's what we have taken it to the right hand side. Again, that I equal to 2, you got this equation. Then I equal to 3, you got this equation. Keep on doing that. At last, you got at I equal to n, and then you got Tn plus 1. So the Tn plus 1 is again your last boundary condition. Fine. So easy to understand, I hope so.
Yes, sir.
Fine.
Yes, sir.
Now,
Yes, sir.
after that, you write it in terms of the matrix, because matrix help me that what should I do. So it will help me always that how do I generate my matrix here. So again, you got a tridiagonal the matrix as you got previously, but elements are different. Previously, यहाँ पे and this side was same, so you got much more comfortable on that particular side. Now here it is slightly changed. It is getting in terms of R also. Previously there were no X coordinate and all this. So you are getting here R and something. So that you need to be generated here carefully. That this one and this one, first and last row need to be is almost same as previous one. Only thing is change of expression. Fine. So I want you to think about this before I show you my own program to you, because until unless you will not think your own, your programming skill will not be developed. Okay, so you develop think for this one today. Write the a program for that. I can give you only with boundary conditions at last year. So if this is your problem statement for this problem to be solved, that you have a steam pipe of length L 4 meter. Inner radius is given 1 centimeter, outer radius is given 5 centimeter. Thermal conductivity is 10, and inner and outer surfaces of pipes are maintained somehow at temperature of T naught 100 degrees Celsius, and T n plus 1 is, or let's say TL, or so that's something TR2, something is 40 degrees Celsius. So you are supposed to find temperature, and this is practically, you can say, transfer of steam or something. Let's say you are maintaining at 100 degrees Celsius somewhere, and outside temperature is 40. So you want to just say typical heat transfer problem in the pipe. Okay. So for this again, you have to solve it, and this is again your analytical solution. So analytical expression of temperature would be this, and heat transfer in a pipe is given by this, right? So try to write the program for that, and tomorrow we can check what you wrote and how can you write it also, and then we will go ahead for maybe for flux boundary condition for this one.
Okay, sir.
Okay, that fine?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
then we will end the class here today.
Excuse me, sir.
Okay, sir.
Yeah.
Sir, we sent some questions regarding non-linear and OD. We mailed you a few days back, sir.
Uh,
So I don't know.
yes, I got all of them, and
Okay, sir.
I have not seen it, and maybe today or from tomorrow only I will start